All right, this video is on finding complex roots. So if you guys recall what a complex number is it's a number, they're written in the form a plus bi. So a represents the real number portion, bi represents the imaginary number portion, and so they're considered complex because they're both real and imaginary at the same time. A root, if you recall, is an x-intercept. Or a zero of the graph. Those are different names for them. So this is looking for solutions to the equation, right? X-intercepts are solutions to polynomial equations, but these are complex because they don't show up on the graph. They're not real. We're not actually going to see these x-intercepts. So this is the process that we use to find complex roots. So I'm going to go through a few different examples so you guys can see them, and then we'll practice them in class. So we have f of x is 8x to the third minus 27. And this you should recognize is a factoring problem, right? This is what difference of cubes is. So I'm going to rewrite the problem setting it equal to 0. And then I'm going to go ahead and factor this using difference of cubes. So I know that this is 2x to the third minus 3 to the third. And then if I factor this, I just remember SOAP, my acronym SOAP. So I have the same sign, and then the first term multiplied by itself. That should not be a 2. And then opposite sign, and then the first term and the second term multiplied, so that's 6x. And then always positive, so I have the second term multiplied by itself is 9. And if you guys recall, I told you that this first one is where we could get our real answers from. That's the factor that actually showed up. And I said that this often did not factor. And one of the reasons it did not factor is because it's usually not even a solution. It's usually with a solution of an imaginary number. So what we're going to do anytime we're left with something like this and we have to solve for x and it's not factorable, we have to do the quadratic formula. So I'm going to have you guys write the quadratic formula on your paper because I find that students don't always have it memorized still. So it's negative b plus or minus square root of b squared minus 4ac all divided by 2a. Okay, so that's the quadratic formula. That's what we're going to plug this into. So I've got negative b plus or minus b squared minus 4 times a times c divided by 2a. And then since I know that this is going to be imaginary, or I'm assuming because it's difference of cubes and they often are, I'm not going to plug all this in at once because my calculator would give me an error message. So I'm just going to go ahead and plug in the part that's underneath the square root. So I have negative 6 plus or minus negative, the square root of negative 108 divided by 8. And anytime I have a negative underneath the square root, I change it to a positive and stick an I in the front. So that's me recognizing that this is now an imaginary problem. And then what I'm going to do is I'm just going to simplify this radical. So 108. This is a very slow way of doing it, but I'm going to be honest, it's how I usually do it. So that's 2 times 27. 27 is 3 times 9. 9 is 3 times 3. So what I can see is I've got a pair of 2's and a pair of 3's and a leftover 3. So that means that when I fix that radical, when I simplify it, I have a 6 out in the front. 3 times 2 is 6. And I have a 3 left underneath. And I can't do anything to simplify the radical because I already did that. But what I notice is that all of these are even numbers, and so I can divide all of them by 2. And that would be my complex roots. There's 2 of them, one for the plus version, one for the minus version. So I did want to show you that because this is a typical case where complex roots show up. Okay, now for a more standard problem, we're going to go through the more recognized process for finding a complex root, depending on our calculator a little bit more than we did in the last problem. So here we're going to have x to the fourth minus 6x to the third plus 6x squared plus 34x minus 195. And so typically, when you're looking for a complex root, they'll give you an equation like this. And what we'll do is we'll use the calculator to find the real roots for us first. And then we'll use those real roots to go through the standard process for finding a complex root. So I'm just going to go ahead and plug this in. My window is normal. You do not have to change your window to see much of the graph to be able to do these problems. So right now it looks like I've got two vertical lines. I know that graphs that are a fourth degree don't look like that. So I know there's more going on, but I don't need to see it. I just need to see the x-intercepts. It looks like I've got -3 and 1, 2, 3, 4, 5. It looks like -3 and 5. I'm going to go ahead and write those down. Now, what I would like you to get in a habit of doing is just verifying that your x-intercepts are right. So for the most part, you're going to get whole numbers. You might get some fractions here that are nice to work with, like 1/2, 2/5, things like that. I'm not going to give you a fraction like 1/48. You know, so but I'm going to check these to make sure that those really are the x-intercepts. So I'm going to hit second trace. Option number 1 lets me plug in any x value that I want into the function. So if I plug in -3 and it is an x-intercept, it should be 0. So it is. If I plug in 5, I get 0, so I was right about those. All right, so I'm going to go ahead and use those x-intercepts, and now the process that I do to find these complex roots is I use synthetic division. So you start with one of the x-intercepts, it doesn't matter which one, and for synthetic division, if you recall, we write down the coefficients for each of these terms. You can always use polynomial long division if you're more comfortable with that. But it's a lot more tedious. So I remember with synthetic division, I always have to drop down the first number. And then with synthetic division, when you're dividing by an actual root, your result should be 0 at the end. You should not have a remainder because the root would go in evenly. So drop down the 1. 1 times -3 is -3. When I add these together, I get -9. -9 times -3 is +27. 6 plus 27 is 33. 33 times -3 is -99. This gets a little more difficult. -65. And then -65 times 3 is 195, which is what it should have been. Next, we use the other real root. And then I take these numbers that I had left over and I set up the process to do it again. So drop down the 1. 1 times 5 is 5. And I add those together to get -4. -4 times 5 is -20. And I get 13. And then 13 times 5 is 65. So it was 0 like I expected. So now these numbers are the coefficient for a quadratic. And I know that these are not real. This would not be factorable. If they were real, they would have shown up on the graph. And so that means that to find these roots that are definitely imaginary, I have to use the quadratic formula. So -b plus or minus b squared minus 4, that's a squared, minus 4 times a times c divided by 2 times a. So I have 4 plus or minus the square root of -36, all divided by 2. And I'm going to make that positive, put an I in the front. This is 4 plus or minus. I don't have to simplify that radical using a factor tree like we did on the previous problem, because I know that the square root of 36 is 6. So now I'm just going to write 6i divided by 2. And both of those numbers are divisible by 2, so I'm just going to go ahead and do that math. That would be 2 plus or minus 3i. And so the complex roots for this particular equation would be 2 plus 3i and 2 minus 3i. So complex roots always come in pairs because they come from the quadratic formula, so they're always like the same thing, one with a plus, one with a minus. All right, I want to show you one last example just of a problem. The process is going to be the same, but I want to show you an example of a polynomial that's missing some exponents. So we're going to do x to the 4th plus 3x squared minus 4. So again, just like with the last problem, I'm going to graph this to find my real roots. And just like with the last problem, I'm going to double check to make sure that I wrote my real roots down correctly. So it looks to me like it's -1 and +1, but I'm just going to double check. So I'm going to do second trace, plug in -1, that one equals 0, so that's a root, plug in +1, that one works as well. So now I can set up my synthetic division, and I'm going to go ahead and do the positive one first this time just so you can see that it works no matter which order you do this. So my coefficient here is 1. I don't have an x to the 3rd, so I'm going to put a 0. I have an x squared. I don't have an x to the 1st, and then I have the number at the end. So what I'm doing is I'm thinking of this function as x to the 4th plus 0x to the 3rd plus 3x squared plus 0x minus 4. And I make sure that when I think of the polynomial function, I have every single exponent, that would be a 1, every single exponent is being used, and I have a coefficient for every single one of those terms. So that's something you have to watch out for. It's not every single problem, but it happens often enough that it will definitely make you frustrated if you run into a problem like that and don't do it correctly. All right, so I drop down the 1. 1 times 1 is 1. I add those together. 1 times 1 is 1. I add those together. 4 times 1 is 4. I add those together. 4 times 1 is 4. And then I'll go ahead and use the other number. I use the numbers that I had resulted with at the end after I did my synthetic division. And I do the process again. So I drop down the 1. 1 times -1 is -1, and I add those together. 0 times -1 is 0, and I add those together. 4 times -1 is -4, add those together, and it equals what I expected it to. So this result is a quadratic. I have x squared plus 0x plus 4 equals 0. Now, if you want to do the quadratic formula on this, you can. But since the b value here is 0, you really could just isolate this x to solve, so that's what I'm going to do. I'm going to say x squared equals -4, because I subtracted it over. And then I'm going to square root each side. And I have to remember that anytime I square root something, I get a plus or a minus. So I have the square root of -4. And I've got a negative under a square root, so I'm going to make that positive and turn that into an I. And the square root of 4 is 2. So I have x equals plus or minus 2i. And those are my imaginary roots.